Hello, everyone. This is the first TCS seminar this year. After a while of break because of our crypto seminar, and today I will tell you about some recent work of mine. It is still, the research is finished. I have not fully written down the paper, but the links I just sent contains a draft of the paper that is almost complete. So what is this talk about? So it is about compressed oracles. And I will first, and actually compressed oracles for permutations. And most of you maybe don't know what compressed oracles are. So I will start with some motivation about what are compressed oracles and what are they for. And then I will proceed to show you my own work. So compressed oracles are something for working with random oracles. So let me recall some things about the classical random oracle model. So in the classical random oracle model, what we want to do is we want to model a hash function. So we have some cryptographic setting, a cryptographic system, which contains a hash function, and we make one idealizing assumption. Namely, we take this hash function, let's call it h, and let's say it maps n-bit strings to n-bit strings, or because I don't want to always write n, let's say from D to D, domain to domain, or in the general case, the output could have a different size, but just to keep it simple, I'm just keeping input and output size the same throughout this talk. So let's say it's a hash function. And now what we do is we model this hash function as a random function. Uniformly random function. And the adversary is assumed to have access to this function. And why do we do that? So what is the purpose of having a uniformly random function as an idealization of a hash function? Well, the advantage is that this makes makes security proofs in many situations much simpler. So one example, it's not an overly challenging example, but I take it as a running example for this talk, is a zero search. So in zero search, our goal is to, or the adversary's goal is to interact with the random oracle and find an input to the random oracle that the output is zero. And we expect that this is hard to do because there are many outputs, so finding one that gives zero has a small probability. But let me very quickly go over how we prove this in the classical setting, because that's the starting point for what we will do throughout this talk. So what I claim is that if we run the adversary has access to the random oracle H, so can make queries, and output some value X afterwards. Then the probability that hash of this value X is zero, this probability one can show is smaller than Q divided by 2 to the n, where Q is the number of queries. So throughout this talk, this will always be the case. And n, 2 to the n, is the output size of the hash function. So how do we prove such a thing? And remember, this is still a completely classical setting. So we don't need to worry about quantum effects or anything. And the technique we use is called lazy sampling. In lazy sampling, so what we do is at the beginning of the execution, instead of saying h is a uniformly randomly sampled function, we say that h is first a completely undefined function. So let h be a completely undefined function, or said differently, the empty partial function. So this is what we do initially. And then whenever the adversary queries the function, so when there's a query h of x, what we do is then we pick a uniformly random element from the range of this function. So any output of the function h is just queried on demand when we need it, and is chosen on demand when we need it, and not in the very beginning. And then it's easy to see, because whenever we query it, we assign a random value. So each time this happens, we have that the probability that the value that we just queried is 0 is smaller or equal to the minus n. Smaller or equal because it could also be that the adversary queries a value again that has been queried before, or maybe it's easier if I just say, oops, where's my eraser? I just say equal, but this is only in the case that a new position is queried. And this means that overall, the probability that there exists a value x such that h of x is 0 is at most the number of queries times the probability that in one of these queries 0 will be chosen. So this bounds the probability of getting a 0 when interacting with a random oracle, which concludes the proof sketch. So this was a very simple example, but in general, this is a very powerful technique, and almost all proofs in the classical random oracle model will use this technique somewhere. It is so ubiquitous that many people actually even define the random oracle just as being a function that is lazily sampled. So what happens if we now look at the quantum set? Well, if we want to use the random oracle model in the quantum setting, first question we need to ask is, how is the random oracle modeled? Because if we are talking about quantum cryptography or post-quantum cryptography, we want security against adversaries that can make quantum computations. And if you do a quantum computation, you can also, if you have a hash function, evaluate this hash function in superposition between many different inputs. So we also need to model the random oracle model as a function that the adversary can query in superposition between many inputs. And this is done as follows. So a quantum query is done by giving the adversary access to two query registers x and y for the input and the output, and then applying a unitary operation uQuery. that is defined to map xy to x, y XOR h of x. And because the adversary can initialize xy with, well, for example, put 0 in y, then you would have here h of x in the output, but you could have a superposition of x's in here, and then you would get a superposition of outputs here, or you could do something more complicated, be entangled with other bits of the adversary state, have something different than 0 here, and so on. So there's a lot of complicated things that the adversary can do, but the basic intuition is that x is the input, and then the output, h of x, will be stored here. But the crucial point is that if you model the random oracle like this, the adversary can perform queries in superposition. And that breaks our lazy sampling approach from above. At least when done naively. Why is that the case? Because above we said when we are queried at one particular position x, then we choose the value for the random oracle at that position, and the rest we leave undefined. But now it could be that we query the random oracle in a superposition between all positions at the same time. What do we do then? Do we, well, if we have then to initialize the random oracle at all these positions, that means that on the first query, if the adversary just does a query of everything in the first query, it means that we initialize the random oracle everywhere in the first query, and we are no better off than if we just had set the random oracle, like picked it at the very beginning anyway, as we do by definition. So it seems lazy sampling doesn't work in the quantum setting. Other problems are if we like keep track of which positions has the random oracle been measured at. This gives us another problem, namely measuring these where a certain input was or what output was given and so on. This could then disturb the adversary state, because the adversary could be entangled with where the input, where the query was made, and doing this measurement will actually change what the adversary does and so on. So we cannot just do that in a way that is not noticed. So for quite a while it was believed that lazy sampling just doesn't work with random oracles, or with quantum random oracles. And I lost sheet 2 of my notes. Here it is. Okay. But a while ago, it turned out that you can actually do some kind of lazy sampling in the random oracle model. So there were Gendry's compressed oracles. And I will not repeat the whole technique from Gendry this because that would get too long, but I will mention the key points. So with Gendry's compressed oracle techniques, you can simulate a random oracle in a way so that the adversary cannot tell the difference, but you can do a kind of lazy sampling. It is more complicated than lazy sampling in the classical world. I mean, almost everything is more complicated in the quantum world. But it gives a lot of post-quantum security proofs that we can do now and that we weren't able to do earlier. And what I will be showing you, one thing I wanted to mention first, one important thing. So it allows us to do a lot of security proofs that we couldn't do before. Sometimes they are even kind of conceptually similar to what you would do classically when you work with lazy sampling. But there's one limitation. It cannot handle permutations. So, well, invertible permutations. So first, what do I mean by invertible permutations? Well, the random oracle, as I've described it so far, we said that H is just a uniformly randomly selected function from the set of all functions from the given domain to itself in this case. If we are talking about random permutations, then it is just a random permutation from n bits to n bits, so a bijective function. Handling random permutations is so far not a problem because there are existing results that say you cannot tell a random permutation apart from a random function. So we know that. However, we might also be in the situation that we want to model a function that has very little structure, but that is a permutation and that is easy to invert. I mean, imagine, for example, a block cipher with a fixed key. You can evaluate, you can encrypt when you know the key, you can decrypt, but that's all you can do. So a possible idealization of this would be to say we model this as a randomly chosen permutation, where the adversary gets access both to the permutation and to the inverse of the permutation. And this cannot be handled with Jeannery's compressed oracle technique because it's purely for functions with that are uniformly random. One can tweak it a bit to cover functions where the outputs are not uniformly random, but still each output has to be chosen independently from all the other outputs. So in a permutation, this is not the case. So far it was not known how to handle invertible permutations. And as far as I know, there is actually no result at all that gives any quantum query complexity or anything for invertible permutations. So we don't know even simple facts about invertible permutations to the best of my knowledge. So it seems that the technique that I'm going to show you today is actually the first technique that allows us to do anything in that direction. Okay, so why are invertible permutation important? Well, one example that I'm also studying in this work is the security of the sponge construction. So the sponge construction is a construction how you construct a hash function out of a block function that takes n bits to n bits. And many implementations of hash functions that use this construction actually are based on invertible permutations. In particular, the SHA-3 hash function. So this is the main industry standard for hash functions, and it uses the sponge construction with invertible permutations. And since we don't know anything about invertible permutations, it means that we knew so far nothing about the post-quantum security of the main hash function that is used in practice. So this is a problematic situation, and with the technique from this paper, I can at least show collision resistance of SHA-3, and maybe other things can be shown in similar ways, but I have so far only covered collision resistance. Other examples why we need that is, for example, if we want to study ideal ciphers, so we want to show that well, we take a block cipher, but idealize it. It's like the random oracle, but for block ciphers. Then for every key, we pick a random permutation. If we want to analyze something like this, we need techniques for random permutations. Or even if we don't want to idealize anything, if we have a proof involving a quantum pseudorandom permutation. So these are cryptographic constructions where if you have a secret key, and if someone doesn't know the secret key, the function is indistinguishable from a random permutation. So the first step in a proof is usually to replace the QPRP by a random permutation. And if this replacement then gives you a random permutation and you have no tools how to handle random permutations, then you are stuck in the proof. So I think that this technique is also very useful if we want to do security proofs that use QPRPs. So-called strong QPRPs. So strong QRPs give access to the inverse. Okay, do you have any questions so far of what I've said so far? Okay, so now I will come to the new approach, which follows to some extent the ideas of Gendry's compressed oracles, but it's the formalization is different, and it turns out the formalization then works both for random functions, but also for random permutations. And I'll first describe it how it works for random functions, because it's a bit easier to think of random functions, and then I will talk about random permutations after that. So the first step is something that is actually taken directly from Gendry's approach, so that's not new. And actually also in Gendry's approach, this is not really new, it's more of that's a standard technique that has been used before. And Gendry calls it the standard oracle. And what we do in the standard oracle is to say, so instead of picking the hash function h uniformly at random and then giving access to it, so instead of saying h is picked uniformly at random from the set of all functions from D to R, and then we give access to uQuery to the adversary, so the adversary can execute this gate where uQuery maps xy to x, y XOR h of x. So this thing we replace by as the initialization. We don't pick h randomly, but we take a quantum register and initialize this quantum register. So it's a really big quantum register. It's a quantum register that is big enough to store the value table of a complete function, of a hash function. So it has, if the hash function goes from n to n bit, this has n times 2 to the n qubits. It's a huge register, but we only need it conceptually. And instead of putting cat h in there, so instead of just saying we initialize this with cat h, where h is a random function, we initialize this with a superposition all functions, and then we have a normalization factor, which is the size of the set of all functions, but it's just a normalization factor. So in this register, we put the superposition of all functions. So it's a register. If we would measure it, we would read out the description of one complete function and completely at random. But we don't want to decide on one. We keep it in superposition. And then we give to the adversary, we give access to a uQuery that is defined a bit differently. It has, again, an input and an output register, X and Y. And the adversary has access to those. But additionally, it takes this register H as an input register. And it performs the following operation. So if the states of X, Y, and H are X, Y, and H, this is mapped to X, Y XOR H of X, H. So we're basically doing the same as up here, except instead of having a classically chosen H, our H is now stored in a quantum register and kept in superposition between all possible values. So using standard tools, we can see that the standard oracle is perfectly indistinguishable from the original random oracle. So this means that instead of using the original random oracle in our model, we can use this standard oracle where everything is kept in superposition. So any questions about this standard oracle? Okay, so why is this useful? Well, take the following example. Let's say we call uQuery, and let's say the register H still has this uniform superposition of all oracles H. And let's say, just for simplicity, we put cat5 on this wire and cat0 on this wire. And also, and then we make a query. And let's say, just to make things a bit simpler, we say we measure what comes out of here. So we will obviously measure 5 here if we put in 5. And here, well, if this was X, 5, Y, and H, 5, 0, and H, then we get here 5, 0 XOR, H of 5, H. And if we say we measure 7, for example, then we know what the state is here, because this projects on the superposition of all functions H, so that H of 5 is 7. So the state we get here is the sum over all H's that satisfy H of 5 is 7, some normalization factor, H. So by having done this query on position 5, we get an oracle, a register that is of the form superposition of all values H of 5 is 7. And at least if you write it in this way, we see that this has in some way now stored the fact where we queried it. Yeah, so this is a very different state than, for example, the state h of 4 equals 7. They're not orthogonal, but they are almost orthogonal. So having this oracle in superposition means that the state of the oracle, even though it faithfully simulates the original random oracle, keeps somehow track of the oracle queries. And this is the insight behind Jean-Marie's result, but this is also what we will use here now. Because the idea is we will describe throughout the execution, throughout the interaction between the adversary and the oracle, we will keep an invariant about what is the oracle state, and we will express this invariant in terms of these kinds of restricted superposition of random oracles. So describe oracle state in terms of restricted H superpositions. So to make this more precise, I will first introduce an auxiliary definition. So for some function f, so this is a partial function, I define cat ff. So this f here is not the same f as here, but unfortunately I cannot write different looking f's with this pen. But this just this is actually a function, and this is just some symbol that distinguishes this from a normal cat. So cat f for the compressed oracle state is defined to be the sum over all h, cat h, but restricted to h's in a certain way. So since this is a partial function, it will for some inputs give us an output, and for some inputs it doesn't give an output. For the inputs where it doesn't give an output, this means that we don't want to constrain the oracle at this place. But for any input where it does give an output, there we want that the oracle also gives that output. So we take the superposition of all values h that are compatible with f. By compatible, I mean that if f is defined on a certain x, then h of x equals f of x. So if f of x is not bottom, then f of x equals h of x. So this is this compatibility definition, and we take the superposition of all those functions and then define with a normalization factor, so that it's actually a quantum state. So far we have not really invented something new. We have introduced some notation. So for example, what we wrote up here can then just be written as the cat f for the partial function that maps 5 to 7. So this means the function that maps 5 to 7 and nothing else is mapped to anything. And then this is then the compact notation to denote this sum. For this sum, I mean, it's not much more compact, but in general, it becomes much easier to write down things if you write down things in terms of these states. So what can we do now with this notation? We can write down constraints on the oracle state or invariants that we claim hold during an execution. So remember, the running example was zero search. We want to search for we want that the adversary wants to find an input to the random oracle that outputs 0. So in an analysis, we might want to express the fact that the adversary has not found an input where the output is 0. So this we can do very nicely with this notation. Whether that's useful, we will see in a moment. But first, let's try to express this fact. Let's say, because this is what we do classically. Classically, we can express that on all the positions that the adversary has queried so far, the random oracle has not returned 0. This can be done in the lazy sampling very easily by just looking at the random oracle as it has been defined so far, because there the random oracle is a partial function, and we can just say 0 is not in the image. So let's try to write down the same thing in the quantum setting now. Well, in the quantum setting, we a invariant for a quantum state would be usually a subspace. So we are saying the state of the random oracle, the state of the register H, is within a certain subspace, and this subspace is the span of all the CADF Fs, where F is a function that does not have 0 in its image. Yeah. So, for example, the state we had up here, this state is written like this, and this function has only 7 in its image. So this state is actually satisfies the invariant. Can I get them at the same time? Yes. But for example, if we would have measured 0, if the query would have given 0, we would have the function, the state 5 maps to 0 cat f, and this would not be in the span. So we do not always, when we query the oracle, will not always stay in the span, but the overwhelming majority of possible outputs of the oracle will be in this span, intuitively. So this is the usefulness of this invariant. And it can be expressed very concisely just by having this abbreviation. Any questions about this invariant? And if we want to be precise, we need to write the invariant slightly differently, because our invariant always has to talk about the whole system, including the adversary register, the X register, the Y register, and the H register. But that can be done very easily, because we just take the tensor product of this space with the full space on E, X, and Y, where these are the query registers, and E is just the rest, like E like environment, but it's the adversary state in this context. So this would be an invariant that says, this says no 0 output was found. Okay, so how can we prove that no 0 output was found? Because this is just expressing something, but this doesn't mean that we can prove that the adversary cannot find a 0. So we need some more tools. So let me give you a proof sketch that 0 search is hard in the quantum setting. I mean, we have seen it in the classical setting before, and now we look at the quantum setting. So in the quantum setting, if we have so what we want to show is that the probability that h of x is 0, where x is chosen at is chosen by the adversary that has quantum access to h, is in O of q square divided by 2 to the n. So this is the bound that we will get. This is not a new bound. I mean, this is well known. Many different proofs how you can prove this, but it's a good illustration of how the technique works. And once we go to permutations, we will actually with almost the same proof get almost the same bound, and that is, to my knowledge, already a new result. So if we want to prove that, first we write down the interaction of the adversary and the oracle as a quantum circuit. So we have 4 wires, E for the adversary state, X and Y for the query registers, and H for the state of the random oracle. And remember, we are using the standard oracle, so this has to be the superposition of everything. As it turns out, with our notation, we can write down the superposition of everything in a very concise way. Because like empty set stands for the completely undefined function. So the function that says undefined on any input. And the set of all functions that are compatible with this is just all functions. Every function is compatible with the undefined function because the undefined function does not put any constraints on the output. So this is just the superposition of everything. So if we put this here, this is exactly what we do in the standard oracle. So this will give us a good simulation of the random oracle. And then the adversary can execute UH, some unitary operation that it wants to choose. So it depends on the adversary. We don't know what UH does, but we know it does not operate on H. And then the adversary performs an oracle query. Oracle query means we run uQuery on X, Y, and H. So what uQuery does, we know precisely. So let me remind you, it maps X, Y, H to X, Y XOR H of X, H. And that's what this does. And then we have the adversary again. And then we have uQuery again. And then we run out of space here, but doesn't matter. This is long enough circuit for illustration. So this is just what the adversary looks like. And now I will, now let's analyze this. So I will look at so remember we had this invariant here, that something is in the span of F's with 0 not in the image. So let's look at the initial state. The initial state has 0F in this last register. So in particular, this is in the span. I will omit this HEXY always just to keep things shorter, but formally it's always there. So this is in the span of all F's such that 0 is not in the image of F. Right? I mean, we know even more. We know that it is exactly the state cat F where F is the empty function, but we don't care. We just say it's some F that doesn't have 0 in its image. So it could even be a superposition of many of them, and later it will be a superposition of many of them. And one more thing that we keep track of is how big F is. So in the beginning, the size of F, meaning how many values are set in F, is smaller or equal 0. It's exactly 0, but we want to write our invariant in a way that is kind of uniform, so that has a similar form in every step. Okay, and now we will go through this circuit step by step and see what changes. So first we apply UA. Since UA only operates on these 3 wires, it has no effect on the invariant. So here we had that the state, okay, let's call this the state psi, like the state of everything is in here. And after UA, the same thing holds. The state psi has changed, but the fact that it's in the invariant has not changed. Now comes uQuery. And I claim that after we run uQuery, we have that the state is now in the span of all f's that still don't have a zero in them. We will come to the fact that you can get a zero answer with small probability, but so we will introduce an error term, but for now I just write it like this. But the size is not zero anymore because we have queried one position. So the size is now at most 1. So this is the new invariant after uQuery. I will come to the error in a moment. And then we apply UA. This doesn't change the invariant, so we have this invariant again. And then we apply uQuery. And now it says that the invariant that holds is it's a superposition of cat f's, so that 0 is not in f, and the size of f is smaller or equal to. And so on. Any questions about this? If you would analyze this circuit, for example, with Hoare logic, these are exactly the kind of invariants you could write in Hoare logic. Except that we will introduce errors, which makes it more complicated, and I haven't tried out whether this fits into the Hoare logics as they are or not, but maybe it does. Okay, now we come to the errors. So here, this holds perfectly. Psi is indeed in this span. However, here psi is not in this span anymore because there's a small possibility that we get a zero output. So when we query at a new position, for example, we may get a superposition between many outputs, exponentially many, and one of them is 0. So we need to bound how much we deviate from this state. And the answer, I will come to how one proves that, but right now I'm saying, giving this the answer. The answer is that this is, psi is not in there, but psi is 4 times square root of 2 to the minus n away from this invariant. So it means psi is not in the invariant, but psi is close to some state that is in the invariant, and this is the distance. And then on the second query, we know that if this invariant before holds, then it holds afterwards with an error. If it holds before with an error, then it holds afterwards with the sum of the errors. So now we have psi is 2 times 4 square root of 2 to the minus n close to this thing. Where close means this is always in terms of the norm. So the norm of psi minus some state in this invariant is bounded by this. And this implies that the final state, when the adversary has run its attack, is 4q times square root of 2 to the minus n far from a zero-free state. So from a state that satisfies this condition. I mean, I'm doing a few things a bit sloppily here, so it actually ends up being a q plus 1 here, but I don't want to go into this in detail. And then it's easy to show that if you are this far from the state, the probability of measuring a zero is just the square of this. So probability of h of x is 0 in the original game is smaller or equal this thing squared, which is the same as 16q squared over 2 to the minus n. So we have analyzed how hard it is to find a zero image, and we have used the new compressed oracle technique. And but one thing I haven't told you yet is how do we find out these error terms? Because how do we know that they are small? And this is actually the main contribution. The main technical contribution is a theorem which I will only sketch here, but it has the main parts here. It says if psi is epsilon close to the span of ket f's, where the f's are in some set A and they are of length at most L, then you query psi, so the state I get after performing a query, is epsilon plus 4 square root of C close to, I will say what C is in a moment, to the same invariant, only that F has become bigger by 1. Oops, I said same invariant but wrote B. I mean, the full theorem is much more flexible, so there can be a different invariant and so on, but I'm trying to keep things simple in this presentation. And this holds, assuming the following, that for all f that satisfy this A, so in our case, for all f's that don't have a 0, that have size at most L, we have that the following bound holds. The number of z's, well, let me first write it. So in order to apply the theorem, we need to show an upper bound on how many z's there are for a given f, so that if I set f of x to be z, so I update the function at one position, how many z's are there that make f, if it was in A before, afterwards not in A? So in our case, if f has no 0 output, how many values of z can make f have a 0 output afterwards? Well, in this case, it's very trivial. There's exactly one value z that makes a 0 output, namely 0. Yeah, the only output, if I set f to have a particular new output, there will be a 0 output only if that output is 0. So this set has size 1, so we get C being 1 over square root of n, and therefore our error grows by 4 times square root of 2 to the minus n, and this is exactly what I had here. So this shows how you do a proof using the this new compressed oracle technique for random functions.
So
yeah,
I have a few questions here. But the C has to be less than 1 over the 2n, right? Or I mean, the C here is, you said that is bigger than the bound. So how you get the Q over 2n?
Well, this one here was 1. In our case, we show that this cardinality is 1. So we have here written 1 over 2 to the n.
Yeah.
And then we see we can choose as long as it's bigger than this. So we can choose C to be 1 over 2 to the n. And this means here we have 4 square root of C.
Okay, so any C that is bigger than this bound is works.
Yeah, exactly. Yeah. So basically C is just the maximum, but you don't have to you don't have to find the maximum, you can find any upper bound.
And this is the proof for the random function. not the
Random
permutation.
functions, yes.
Because for the random permutation, probably the initial state in the Oracle register has to be different.
Yeah, so for random permutations, it follows, it's very similar, except that everything needs to be done like a little bit different.
But how the initial state has to be generated in the Oracle register?
You mean how to implement that?
Yes, well, in case of the random function, it's just 0 in a Fourier basis. But when we have a permutation, then the initial state is difficult to get.
It is difficult to get. I will come to the permutation in a moment. I mean, right now I haven't talked about permutations yet. I will come to it, and if your question is still there, let me know.
Yeah, one more question. In the circuit, not necessary UA is not necessarily the same because in the circuit that you draw in the
it is a matter of how you model the adversary. You could say it's always the same because the adversary can, without loss of generality, have some counter in its register to know where it is, or it could be a different one each time. I've written it with always the same, but if you prefer to have it always different, the technique doesn't change. I mean, it's because the argument was just UA doesn't change the invariant.
Okay, yeah, true. Mm-hmm. Right, thank you.
Okay. Okay, so now, where was I? So far, nothing is really new. We have a different technique from Jandry. Like it's a bit different. It takes the, it doesn't do this. So Jandry, I mean, this is more for those who know Jandry's technique. So in Jandry's technique, we take the state and transform it into a different representation in which we can read off this partial function very easily. And it may look at the first glance that this is the same because these cat FFs that I have, they look similar. But just for comparison, in Jandry, if we have the state, like for example, the sum of all h that are 7 with some correction factor. So for this example state that in our setting was just cat FF with 5 maps to 7 would in Jandry be, by the operation introduced by Jandry, mapped to the state oh no, it's the other way around. Sorry, I wrote it the wrong way around. So if in Jandry we write something like we have the state 5 maps to 7, in Jandry's notation, it's a database that has the pair 5 and 7. So this does not map to this superposition of all h's with 5 maps to 7, but instead it maps to this state, which is what we actually mean, plus 1 over square root 2 to the minus n, the sum of all h's that are bottom at that position, minus 1 over 2 to the minus n, the sum of all y. That's nonsense. Wait, this, and the sum of all h's. So it's a and this thing does not really have much intuitive meaning. It's just some term that makes things more complicated. The reason why it's needed in Jandry's case is that the transformation that Jandry applies, because it does a bijection between unitary between these compact representations and the standard oracle, it has to be unitary. So all those states have to be orthogonal. And without this thing in the circle, which I call the correction, things are not orthogonal. But with the correction, all those states become orthogonal, which is important for Gendry's technique, but makes this thing much harder to interpret. Because what does it mean? It does not mean 5 is known to be 7, because 5 could be also mapping to something else, just with a small amount. So understanding Gendry's invariance is harder than in the approach that I showed. So this is one big difference. But the results we get are the same, although there are also limitations in my technique, because it does not, we cannot efficiently measure this function. So, for example, the indifferentiability proofs that are done in this framework, I don't know yet how one could do them in my technique. So this as a side comparison with Gendry. Especially to point out that it's not the same, just written with different notations. So now I can finally come to the permutations. So first, let's rethink the idea of the standard oracle. Because we want to do everything the same as before, only for permutations. So before in the standard oracle, we had the initial state of the oracle. And we had said it's the superposition of all functions h. But now it's just the superposition of all permutations from d to d, and then divided by how many they are. So this is the initial state. Yeah? It's not initialized with a random function, it's initialized with a random injective function, or if input or output domain is the same, meaning a random injection. And then when the adversary performs a query, we use the unitary uquery that we had before, so nothing changes there. It maps x, y, h to x, y XOR h, y XOR h of x, h. No change. But of course, we wanted to have invertible permutations, so we also have to give queries to the inverse. Now I could just define a u query to -1, which would be would have h to the -1 here, but I choose a slightly different modeling, but that is equivalent in adversary powers. I give the adversary an oracle that does not query the random oracle, but changes the random oracle. It just inverts it. So if we want to query the inverse, you invert the random oracle, query it normally, and invert it back. So this function invert just maps any cat h to cat h to the -1. Why do I do that? Well, it's equivalent in power, and it is somewhat more convenient to explain the ideas of the technique by splitting into the query and invert. Because we will get the invertible part almost for free in this approach. And now the invertible standard oracle is equivalent to the original invertible permutation oracle in the sense that the adversary cannot tell the difference between the two. And now the next step in our approach was that we defined these states that are superposition of h's up to a certain constraint. So we had defined this ff earlier, but now I defined a state fp, where p stands for permutation. And this is defined as the superposition of all h's, where h is an injection and h is compatible with f. So instead of taking all functions that are compatible with this partial function f, we take only the injections that are compatible. And then here's some normalization factor. So for example, the empty function cat empty p is just the sum over all, it's a uniform superposition of all permutations H, which is exactly the initial state that we had here. And now we can do the same kind of proof as before. So if we ignore invert for the moment, so let's say we are interested in the in a permutation oracle, random permutation, but not an invertible one, and we want to know how hard is it to find a zero, and then we get that the probability that h of x is 0 if a gives us if a has access to h but not to the inverse is again in q square over 2 to the n if h is a permutation. And the analysis is exactly the same, except you start with this state here. You represent the, so if I go up again to this analysis, where did it go? Here, you, instead of writing a little f here, you write a p here, because now our invariant is expressed in this p states. The bounds here are a little bit different, but the difference is so small it vanishes in the O stuff. And the important part is that the same kind of main theorem also holds with an p here. Then the bound here becomes a little bit different. So there are like minor differences here and there in the concrete values, but it does not change the overall behavior. So you get almost the same bound with the same proof. Of course, the theorem, it doesn't follow from this main theorem. So we have a main theorem for random functions. We have a main theorem for random permutations. They just happen to be very similar. Does this already answer your question, Essa?
Yes, but what about the if we want to implement the initial state? There's a way to do it? Well, this is...
You mean efficiently implement it?
Yes, because in case of random function, it's just the Hadamard to the 0. So
yeah,
but here we have a permutation.
Saying it's just Hadamard to the n is also a bit misleading, because that's still not efficient. I mean, if you want to write down the if you want to do this transformation on each output individually, you need to do exponentially many Hadamards. So it does not really matter whether it has its exponential time and easy to understand, or exponential time and hard to understand. So in that respect, it's it doesn't really matter whether this cat empty is easy or hard to do, because it's exponential anyway, and we just use it as a tool in our analysis, and we don't implement it. Of course, in the Gentry case, what we can do there is we can keep the state in a compact representation, like not the whole value table, and do this decompress, query, recompress in one query, and we can implement it without decompressing everything, and so on. So there's there's an efficient way to simulate a query when we keep the state in the compressed representation. So this is something that's different here. We have no way to efficiently simulate the permutation oracle. At least I haven't found one yet. But for example, for this proof here, we do not need that. We do not even change the oracle. So in Gentry's case, we always convert back and forth, and we keep the oracle. In this compressed representation. In my approach, we keep the oracle in the standard representation, but we just write the invariance in the invariant using these compressed states to keep track of what the adversary achieves.
Yeah. And this, your technique is to get a probability of outputting is like pre-image of 0, but it doesn't actually, does it also can be used to record the queries for random permutation or not?
I mean, it depends what you mean by recording. I mean, the invariant, you will have an invariant that has a list of the queries. But if you mean that you want to efficiently access it, so for example, you want to make a simulator that looks at what has been recorded.
Yes.
This I have not solved. Maybe it's possible. I don't have an impossibility, but I don't have a solution to that either. So there are some things that I cannot do that can be done with Jandri's technique.
Yeah, there was a recent work by Schaffner, I guess, that quantum lazy sampling, and they claimed to do it for random permutation as well.
Yeah,
and
they claimed it kind of halfway, and then they don't claim it anymore now. So
okay.
Jan just came in. You can ask Jan.
Hi.
Hi.
Yeah, we
one of the authors.
wrongly claimed it. Sorry for that.
Yeah, all right.
Okay. Yeah. So. Okay. So this shows what I just showed is that with a random permutation, you can, if you get oracle access to random permutation, you can find a zero pre-image with probability at most q square over 2 to the n. This may not seem very new because we know that random permutations without inverse are indistinguishable from random functions. And for random functions, we already know that this is the upper bound for the query complexity. However, the indistinguishability between random functions and random permutation gives us an additional error. So we would get a q to the 3 here. So having it with this exponent is, to my knowledge, also already new. But it's still not that exciting because it's not about invertible permutations. So let me come to the invertible permutations then. So as I said before, for invertible permutations, we have the additional oracle invert that just flips the random oracle around. And now the adversary, during an execution, can either do a normal query, and we have the main theorem that tells us how the invariant evolves, or the adversary can perform a invert query which flips the oracle around. So we need to ask what happens to the invariant when the oracle is flipped. Well, for this, we need to just know what happens if we apply invert to cat fp. And we know what happens if we apply invert to cat h, so to an uncompressed state, but this superposition state, what happens if we apply invert? And the answer is actually exactly what one would hope. If we apply invert to a compressed state, it's the compressed state for the inverted partial function. So not very surprising, and the proof is also just a few lines. So this is extremely simple. And this means invariants are simply inverted when we run invert. So to put all this together, let me do one more example analysis. What I call two-sided zero search. So what we want is, so let's say we have an invertible permutation, and we want to find an input x, so that if I input x concatenated 0, I get some y concatenated with 0. And let's say this upper part has r bits and the lower part has c bits. So before I asked for something that gives me a complete zero here, but I had full freedom here. Now it's kind of half-half. I want to input something that is half zeros, so that it also gives an output that is half zeros. Because the zero search thing is boring in the permutation case. You do one inverse query and you have the answer. While this is a problem where there's no obvious way how to solve it with inversion queries, but it's also very hard to see that it's not solvable. So this is something which already years back with Alexander Belov's, we tried solving this thing and we failed. So using things like the adversary technique or the polynomial method, all these standard approaches, they all failed. And the reason why we looked at this is a special case of the security of the sponge construction. So it's easy to see that if you can find such a thing, you can completely break the sponge function. Not the other way around, but this seemed like a good starting point. And we already got stuck on this on that one, which is the reason why so far all post-quantum analysis of the sponge function, they were all only for random functions and not for invertible permutations. I mean, they're also for non-invertible random permutations, but not for invertible ones as we would need. So this is the query complexity problem that we want to analyze. And if like an X and Y that have these this form, we call a bad pair. So we want to show that the adversary cannot find a bad pair. And again, the approach is that we write down a circuit with wires E, X, Y, and H, with H being the oracle. We initialize H with cat empty P, which is the superposition of all permutations. And we have our initial invariant that says we are in the span of all Fp so that F has no bad pair and the size of F is at most 0. Yeah, so for the initial state, this is obvious because F has no input outputs at all, so it can also not have a bad pair input output. Now, for example, if we run UA, since this does not operate on H, it does not change our invariant. Then we may ask what happens if we run uQuery. This gives us a new invariant that looks almost the same. Except that the bound for the size will now become 1. And there's an error term. So in order to compute that error, we need to bound how many values z will update a function to have a bad pair. So to get the error here, we need to find the following bound. If f has no bad pair and the size of f is smaller equal well, some value L, depends in which query we are, then we want to bound how many z's are there so that f with x updated to be z has a bad pair. So this was the thing, remember in the main theorem, going there, here, we needed to show this bound. I mean, now we're using the main theorem for permutations, but the upper part is basically still the same. So, and there it said, so we need to count how many outputs z can switch a function that has no bad pair into one that has a bad pair. And this divided by n minus 2l. So that's this minus 2l is new because of the permutation case. but L is much smaller than N, so it doesn't make much difference. And we want that this is smaller than C. So how many Z's can make something into a bad pair? Something can only be a Z bad pair if it starts with 2 to the R zeros, because a bad pair is, no, it has 2 to the, it has to end with C zeros. So the only Z's that make a bad pair are the ones that ends in C zeros. So they are only R bits free. So we get roughly 2 to the R divided by, actually this should be the size, so divided by 2 to the R plus C, which is 2 to the minus C. So this means that this new invariant now holds with an error of 4 times the square root of C, which was 2 to the minus R. And this we can do the same thing again and again with, I mean, roughly, I ignored this thing. This we do with every U query. And the last thing that is of interest is invert. Oops. So what happens if we do an invert query? Well, the invert query will map cat f into cat f to the minus 1. So it becomes this invariant, but saying f to the minus 1 has no bad query, no bad pair. But f to the minus 1 has no bad pair if and only f has no bad pair, because it's symmetric definition. So we actually get that the invariant is just preserved by invert queries. So therefore free. In other settings where the invert is not symmetric, you actually change the invariant back and forth between a forward and a backward version. But in this example, we are fortunate that it's even easier. So taking all this together, we get that the final state is roughly 4q square root of 2 to the minus r close to the invariant, and therefore the probability that that we find a bad pair is bounded by the square, so q squared divided by 2 to the minus r, by 2 to the r. This was an analysis of the two-sided search problem. And very similar analysis can be used actually for the full sponge construction. I don't have time to tell you about it, but I just tell you the final result. Sponge, the probability of finding a collision is then in O of q to the 3 divided by 2 to the minimum of C. This is the so-called capacity, so the part of the inner size of part of the inner state, or D, whichever is smaller. D is the output size. For the SHA function, D is always smaller. So so for example, for SHA-3 512, we get Q3 divided by 2 to the 512, which means you need around 2 to the 170 queries to break it, at least in the generic setting. Yeah, so that concludes what I wanted to say. So do you have any questions? Okay, if there are no questions, then I would like to thank everyone for your attention and see you next time.